Hello everyone, let's analyze. So today we're going to continue talking about limits. There's nothing like them. Well, because they're unique. In fact, it's a theorem. If a sequence converges, then it has a unique limit. We now actually have two definitions of a limit. So then there are actually two ways of proving this. You thinking what I'm thinking? Let's do both. Exactly my thought. First proof. So here's the idea of the first proof. Since every neighborhood of a limit L contains all but a finite subset of the sequence, then there exists a neighborhood around every other number containing only a finite number of sequence entries, denying every other number a chance at being a limit. So we see this illustrated in an example below. L is the limit and M is another number. I can let H be half the distance between L and M. Then the H neighborhood of L, in other words, L minus H to L plus H, that open interval, contains all but a finite number of sequence entries. Since the H neighborhood around M is not contained in the H neighborhood around L, that neighborhood of M must only contain a finite number of entries, which means it's impossible for it to be a limit. So here we're using the neighborhood definition of a limit. Okay, so let's move that picture up and let's put the idea of the proof into a rigorous language. Suppose L is our limit, then every neighborhood of L contains all but a finite number of sequence entries. Suppose M is not L and H is half the distance between L and M. Then the H neighborhood of L, in other words, the open interval L minus H to L plus H, contain all but a finite number of sequence entries. This implies that the complement of that H neighborhood of L, which contains the H neighborhood of M, contains only a finite number of sequence entries. And since M, which is not L, is an arbitrary non-L number, there exists a neighborhood of it that does not contain an infinite number of sequence entries. Therefore, M can never satisfy the neighborhood definition of a limit. Well, that was a pretty proof. It even came with a picture. So how would we prove it another way? In this way, we'll use the traditional, for any epsilon greater than 0, there exists a natural number definition of a sequence limit. Let epsilon be greater than 0 and arbitrary. Suppose AN converges to L and AN converges to K. Now, we're going to prove, of course, that L and K must be equal, but so far, L and K are just limits of a common sequence. Well then, by definition of what it means to converge, there exists both a natural number big N and a natural number big M that guarantees that AN is arbitrarily close to L, specifically half of epsilon. So the difference between AN and L is half of an epsilon, and the difference between AN and K is also half an epsilon. In order for AN to be within half an epsilon of L, we need N to be greater than or equal to this big N. Again, we know we're guaranteed that the big N exists because of the definition of convergence. And AN is within half an epsilon of K so long as little n is greater than or equal to big M. And again, big M's existence to guarantee this comes from the fact that we're supposing that AN converges to both L and K. Now, from the definition, we know that we can make that difference less than any epsilon. So why did we put epsilon over 2 instead of just epsilon? Well, eventually we're going to show that if AN is within half of epsilon of L and half an epsilon of K, then L and K are within epsilon of each other. Okay, that's what we're working towards. But why can we say epsilon over 2? Because remember, the definition of convergence begins with for any epsilon. For any, right? Meaning, for any number, I can take half, and the definition of convergence will still works. That for any epsilon is a really crucial, important part of the definition. So the next step is we're going to let P be the larger of the two natural numbers, big N and big M. The idea behind P is we want to guarantee that AN is within half an epsilon of both L and K, because P is either N or bigger than it, or M or bigger than it. Once we've selected our P, we're going to add 0 just so, and put our triangle inequality to good use. So of course, the difference between L and K, in absolute value, must be a non-negative number. And if I add 0 by adding and subtracting AP, and then use my triangle inequality to split this here, I get this is less than or equal to the difference of L and AP and K. Now, I know that this difference is less than epsilon over 2, right? It's true for every index greater than M and greater than N, and P is greater than or equal to both N and M. So I can say that both of these terms are less than epsilon over 2. And of course, half an epsilon plus half an epsilon is 1 full epsilon. Therefore, the difference between L and K is both greater than every negative number and also less than every positive number. Well, the trichotomy axiom implies that the difference must be 0. And if the difference is 0, that would imply that L equals K, and we have our proof. So we've proven the theorem in two different ways. One using the neighborhood definition of a limit, and one using the for any epsilon there exists a natural number definition. So which one is prettier? Okay, let's have a vote. Raise your hand if the neighborhood proof is prettier. Okay, now raise your hand if the for any epsilon there exists a natural number definition. Okay, so keep your hands in the air. Let me count. Oh, really? So there is a clear preference for that proof. You know, I have to say I like the other one better, but to each their own. Now the next theorem says that if a sequence converges, then the set of all of its values is bounded. Now, let's briefly discuss the subtle difference between this mathematical object and this mathematical object. This one is a sequence, which means it's an ordered list which goes on forever, whereas this is a set of numbers. This sequence goes on forever. This set is unordered and could possibly be finite. It's basically just the set of every value assumed in the sequence. Okay, so let's prove that if the sequence converges, the set of all of its values is bounded. Since the sequence converges, it has a limit. We'll call it L. All but a finite number of sequence entries are contained in a 1 neighborhood of L, meaning the open interval from L minus 1 to L plus 1. Right, that's guaranteed by the neighborhood definition of convergence. Now, let's consider the finite number of sequence entries outside of that 1 neighborhood of L. Because there are only finitely many numbers outside of the neighborhood, that set of numbers must be bounded because all finite sets of numbers are bounded. It's like asking who's the tallest person in a room. Unless there are an infinite number of people in a room, someone's tallest. Now, the infinite entries found between L minus 1 and L plus 1 are, of course, bounded by, well, L minus 1 and L plus 1. Therefore, every single entry is bounded, those inside of my 1 neighborhood and those outside of my 1 neighborhood. So, all the entries are bounded. We've proven our result. So let's take a look at some examples of a sequence and then the set of values. If I have the sequence 1 over n, from n equals 1 to infinity, then the set of sequence values is just every number that can be expressed as 1 over n, where n is a natural number. So the sequence is an ordered list, whereas the set of values is every number in that ordered list, but without order. But of course, they really can both be expressed the same way. The sequence can be expressed 1, 1/2, a third, a fourth, a fifth. And the set, of course, you can write it in order if you want, and you could write the set as 1, half, a third, a fourth, and so on. Now, if we apply the theorem to this sequence, we know that the sequence 1 over n converges to 0. Therefore, the set of all numbers that can be expressed as the reciprocal of a natural number is bounded. Now let's consider the sequence cosine of n pi. Now remember that cosine is the x-coordinate of a unit circle when I index by angle of the radius and the positive x-axis. So when n is 1, or any odd integer, I'm at the left side of the circle, and cosine, that is the x-coordinate there, is -1. And for even values of n, I'm at multiples of 2 pi, so I'm at the right hand of the circle, and the x-coordinate there is 1. So this sequence would be -1, 1, -1, 1, -1, 1, repeating forever. However, if I were to construct the set of all values, there's only 2 values in the sequence, 1 and -1. So while the sequence may go on forever, for example, there is a millionth entry in the sequence. It's 1, by the way. The set of all values generated by the sequence only has 2 entries, 1 and -1. Now, warning, the converse of the theorem above is not true. In other words, this is not an if and only if statement. If the set of sequence values are bounded, we cannot conclude that the sequence converges. So in this example, the set of sequence values is in fact bounded because it's a finite set. However, the sequence does not converge. Remember that the converse of a logical statement A implies B is that B implies A, and that's not true here. However, the contrapositive is true. Not only is it true, it's actually quite useful. In fact, we'll call it a corollary all on its own. Remember, the contrapositive of a statement A implies B is not B implies not A. Remember, a way to think about that is every time A happens, B happens. Meaning if B never happened, then A could never have happened. And that's essentially what we have here. If the set of values is not bounded, which you call unbounded, then the sequence diverges. Because had the sequence converged, then the set of values would have been bounded. So let's move that corollary up and let's give an example. Let's use this corollary to prove divergence of a sequence. So let's let A1 be 1, A2 be 1 plus half, A3 be 1 plus half plus a third, and in general, let AN be 1 plus a half plus a third plus a fourth plus a fifth, all the way up to a nth, or 1 over n. This sequence is called the harmonic series. So the strategy here is we're going to show that this sequence has a set of indices with sequence values that grow unboundedly, grow arbitrarily large. So let's consider the sequence entries indexed by a power of 2. In other words, A2, A4, A8, A16, A32, A64, so forth and so on. Now, A subscript to power of 2 is 1 plus half plus a third plus a fourth plus a fifth plus a sixth plus so on and so forth until I get to 1 over 2 to the n. Now let's regroup. Let's consider 1 plus a half as a term, a third plus a quarter as a term, a fifth plus a sixth plus a seventh plus an eighth as a term, and so on. So how exactly am I grouping them? Well, notice the jth term is just the sum of 1 over the previous power of 2 plus 1 through 1 over the current power of 2, the jth power of 2. So for example, a third plus a quarter is 1 over 2 to the 1 plus 1 plus 1 over 2 squared, and that's the second term. See, this is the second term here. So I go from 1 over the 2 to the 1 plus 1 over 2 squared because it's the second term. Consider the third term. I'm going to add from 1 over 2 to the 3 minus 1, in other words, 2 squared plus 1, that's 5, 1 over 5, plus a 6 plus a 7th, and because it's the third term, I'm going to end at 1 over 2 to the third power. And so that's this term. And so I'm going to split the terms in this way. So notice the length of this term is 2 numbers. The length of this term is 4 numbers. The next term would have 8 numbers. The one after that would have 16 numbers, so forth and so on. So by demarking terms in this way, it makes it simpler to notice that we can bound A to N below by, well, this first term doesn't change. This second term, I'm going to get something less by replacing a third with a quarter, right? Since 3 is less than 4, a third is greater than a fourth. So because I replaced the third with something less, right, I'm getting a lower bound, something less than, right? This is, from this perspective, this is less than A subscript 2n, which is what this is equal to. Here I'm replacing a fifth, a sixth, a seventh, all with 1/8 because 1/8 is less than 1/5. It's less than 1/6, it's less than 1/7. I'm going to do that all the way through, right, even until the last one where I replace 1 over 2 to the n minus 1 plus 1 with 1 over 2 to the n all the way through. So I've changed the number, but I've specifically changed it by making it smaller, giving me a lower bound for A subscript 2n, 2 to the n. Well, this didn't change. That stays at 1 plus a half. A quarter plus a quarter is 2 quarters. An eighth plus an eighth plus an eighth plus an eighth, that's 4 eighths. And I'm going to keep doing that. Remember, the next term would have been 8 entries, and I would have replaced all of them with 1 over 16. So I would have had 8 sixteenths, which again would have been a half, all the way through here. Now, of course, 1 plus half, that remains. 2 quarters, that's half. 4 eighths, that's half. If I had gone on, this would have been 8 sixteenths, that's half. This also is half. I get 1 plus half plus half plus half plus half plus half. In fact, I get n halves. So that's equal to 1 plus n over 2. So 1 plus n over 2 is a lower bound for entries of my sequence corresponding to a power of 2 index. So since a 2 to the n is greater than 1 plus half of n, but 1 plus half of n grows arbitrarily large. 1 plus n over 2 can be as large as I want it to be. That means the set of sequence values, right, all sequence entries, including these, is unbounded, because there's no way that I can bound this term. It grows arbitrarily large. Half of n plus 1 can be as big as I want it to be. So my set of values is unbounded. So using this theorem, the fact that my set of values is unbounded, that implies that the sequence an, that is the harmonic series, diverges. So now we know that if a sequence converges, its limit must be unique. The set of all values assumed is bounded. And if the set of all values assumed is unbounded, then we can use that to prove that the sequence necessarily diverges. Well, that's it for today.